The next topic we want to look at is cavitation and net positive suction head. To understand cavitation, we want to go back to the basic Bernoulli's equation. And remember that when the velocity of fluid increases, the pressure decreases. So if we're in a situation where the velocity has increased so much that the pressure of the liquid drops down to the boiling point, then that's cavitation. We get a vapor bubble forming in our liquid. So if P falls below the vapor pressure, which is also the saturation pressure, the liquid will boil. This is a really big problem for pumps because it can potentially cause severe damage in the pump. It causes unsteady flow. We have vapor bubbles forming and disappearing, and so pressure changes are very, very erratic. It causes a lot of vibration, and in a large pump that can cause very, very big problems. And the most significant damage is erosion damage on the impeller blade. Now this doesn't actually happen when the vapor bubble forms. It actually happens when the vapor bubble collapses. It's the collapsing vapor bubble on the surface of the impeller that causes erosion damage and the classical cavitation damage. So we need to make sure that this pressure does not drop so low that the water begins to boil. So as the liquid enters a pump, it accelerates. So the velocity goes up and the pressure goes down. So we need to make sure that the pressure at the pump inlet is high enough that cavitation will not happen. So that as the pressure drops within the pump, the pressure doesn't go down lower than the vapor pressure. So this brings us to the idea of net positive suction head. So the definition, first of all, of net positive suction head, it's the difference between the absolute stagnation pressure and vapor pressure at the pump inlet. And by tradition, this is expressed as a head. So we're actually talking about pressure here, but we're expressing it in units of head usually. So here's net positive suction head, and the four letters NPSH are used to denote net positive suction head. So this is the absolute stagnation pressure, so it's the static pressure plus the so-called kinetic pressure, but expressed as a head. The subscript I there refers to the fact that these conditions at the pump inlet is what is important. And then PV here is the vapor pressure. So at any particular temperature, whatever substance is being pumped, water usually, will have some vapor pressure. Now there are two different numbers for the net positive suction head. One is a characteristic of the pump and one is a characteristic of the piping system. So the first of these that we're going to talk about is NPSHR, or net positive suction head required. That's a characteristic of the pump. So when we're purchasing pumps or looking at pump curves, there will be information in there on the NPSH requirements of that pump. So this is telling us for this particular pump design, what positive head does it need at the inlet to make sure that cavitation doesn't happen within the pump. So it's given on pump curves, and we will see that information when we look at more sophisticated pump curves later on. And it depends on what liquid is being pumped, what temperature that liquid is at, and what the flow rate through the pump is. So it's shown on pump curves because the pump curve is pressure as a function of flow, and so this can be shown quite nicely on there as well. NPSH available is actually a characteristic of the piping system. So for a particular piping system configured in a particular way, how much positive suction head does it provide to the pump at the inlet? So NPSHR and NPSHA, one a characteristic of the pump, the other a characteristic of the piping system. And we're going to look at both of these. Now first of all, we want to look at the available net positive suction head. So this is the one that's a characteristic of the piping system. So take a look at this little schematic here. We've got an open reservoir, an exit from the open reservoir going into the suction side of the pump, and then the discharge side of the pump heading off to supply some piping system. And the reservoir is open to atmosphere as it usually has been. We want to write Bernoulli's equation from the surface of the reservoir to the inlet of the pump. So we're going to label this number 1 Normally we might label this number 2, but I want to be specific that it's the inlet of the pump we're talking about, so I'm going to use the subscript I to denote that location. One thing that's important is the elevation of the pump inlet relative to the surface of the reservoir. So we'll call that Zi. We're going to have our datum, or our Z equals 0 here at the surface of the reservoir. So this particular configuration, Zi would be a positive number of some magnitude. So here's Bernoulli's equation with losses written from the surface of the reservoir to the inlet of the pump. And we've written it like that because we know the definition of net positive suction head involves this quantity here, the pressure and velocity at the inlet to the pump. So we want to have those quantities show up because this is part, at least, of the NPSH showing up here. As usual, we'll make a couple of simplifications to this equation. We'll say that this is a large reservoir so that V1 is 0. And we've already talked about the fact we're going to put our datum at the surface of the reservoir, so Z1 is also 0. Now usually at this point we would also cross off this term by saying that P1 is 0 gauge. However, because we're working with cavitation here, we need to express our pressures in absolute pressures because the saturation pressure or vapor pressure will be an absolute pressure. So we need all these pressures to be in absolute. So we can't cross this off, but we will let P1 be equal to atmospheric pressure because point 1 is exposed to atmosphere. So this is what we have left. We have atmospheric pressure, that used to be P1. And on this side, we have the static pressure and kinetic pressure at our inlet, expressed as a head, the elevation of the inlet, and the head loss. Now we'll just set that aside for a moment, and we want to recall our definition of net positive suction head. So net positive suction head, and we're working here with the net positive suction head available, is equal to the static pressure plus the kinetic pressure. So together those are the stagnation pressure, but they're expressed as a head because they're divided by rho g. So it's that stagnation head minus the vapor pressure expressed as a head. So that's our definition of NPSH. So notice that these two terms are common to both of these things. So we want to get rid of these and substitute in NPSHA plus PV. So just rearranging this second equation, taking that and putting it on the other side, we now have this separated out. So we can take that and put it in here. And that's the last thing we want to do here. So we now have atmospheric pressure, NPSH available, vapor pressure, elevation, and head losses. So what we want to get out of this is an expression for NPSHA. So we're just going to put that alone on the left-hand side of the equation. So this tells us a lot about the things that we can do to our piping system to prevent cavitation. The basic idea here is we want to do whatever it takes to make this as large as possible. Because the bigger we have this, the safer our pump will be, because the available net positive suction head is bigger. So we want that to be big. Well, everything on the right hand side here, these three terms are all making that smaller. So they're all subtracting from this atmospheric pressure. So there's three things here that we can change or we can influence perhaps to prevent cavitation. First one we see here is the vapor pressure. So this vapor pressure depends on temperature. Certainly it depends on what type of fluid we're pumping as well, but presumably we don't have a choice there. So the temperature does have an effect here. So the higher the temperature is, the higher the vapor pressure will be, and therefore the lower the net positive suction head will be. So pumping cooler fluids is safer than pumping hotter fluids, because hotter fluids are going to boil more easily, essentially. So low temperature is better than high temperature. The second thing we see here is the elevation of the inlet of the pump. Anything we can do to decrease this will increase NPSHA. So we want this to be as small as possible. So let's take a look at that. This is our sort of default configuration that we started this off with, and the inlet of our pump is at some elevation, in this case above the surface of the reservoir. Well, a much better configuration and a much better location for the pump is to move the pump down. And in general, we want to mount pumps as low in piping systems as we can so that the pressure at the inlet to the pump is as high as possible. So this change to this system is very, very good in terms of increasing the NPSHA. This ZI is actually negative. Remember, we established our datum like that. So this ZI, we've reduced the elevation quite a bit, so we'd be putting a negative number in here, so we'd actually be increasing NPSHA. But the main thing here is move the pump down, decrease this, and increase this. So that's one thing we can do to the configuration of our piping system to keep our pump safe from cavitation. The last term that we see here is the head loss term. And again, anything we can do to reduce the head losses in the suction side of the pump is going to increase NPSHA. Now, the other thing to remember about head loss is that that changes as the flow rate changes. So the higher the flow rate through the pump, the larger the head losses will be in the inlet section of the pump. So as Q increases, this is going to increase and cause larger problems. So as Q increases, our NPSHA will decrease. So let's illustrate that as well. So this again is our starting configuration. The only change I've made here is I said, well, I want to be able to control the flow rate through this system. So I'm going to put a valve right here. And if I want to reduce the flow rate, I can partially close that valve and reduce the flow rate being supplied to the piping system like that. Well, this is a really bad idea. We would never put a control valve or a restriction like that on the suction side of a pump, because what we're doing as we start to close that valve, we're increasing the minor loss coefficient associated with that valve, so we're increasing the head losses between the reservoir and the inlet of the pump. We're increasing this, therefore we're decreasing the NPSHA, and that could cause cavitation because we're reducing the pressure at the inlet. A much better location, and the conventional location for a control valve, is on the discharge side of the pump. You'll often see valves on the suction side, but they're just there so that we can close them off and isolate the pump, change it out perhaps without having all the water drain out of the reservoir, and they would normally be completely open when the pump is operating. So a control valve that is going to vary the flow would be located on the downstream side of the pump. Now, what that's doing is keeping this head loss as low as possible so cavitation doesn't occur. Now we want to start to look at net positive suction head plotted as a function of flow rate. So notice these are the same coordinates as we use for pump curves. We have head on the vertical axis, sometimes it's pressure, sometimes it's head. Here the units will be head, and flow rate on the horizontal axis. Well, the quantity we've been talking about so far is the net positive suction head available. And we've seen, because of the increasing head losses, that NPSHA decreases as Q increases. And this decrease, this drop off that we're seeing here, is due to the head losses increasing. The fixed portion of it here is due to the elevation of the pump and the vapor pressure of the fluid. So there's a fixed portion and a variable portion. Now, if we take a look at pump characteristics, if you look at pump curves, which we will be doing later on, you'll see that they have a line on them labeled NPSH. And that's the NPSH R, or the required NPSH. So that's a characteristic of the pump. The pump manufacturers have done some testing with their pump to determine what net positive suction head it requires, and they've plotted that on the pump performance curve for us to use. So those lines will look something like this. So the way that this works is those two curves cross at a particular flow rate. So if the actual flow rate through our system is less than that, then cavitation will not occur. Because if we're at this flow rate, it means our NPSH-A, the available head at the inlet of the pump, is there, and the requirements of the pump are down here, so it has more net positive suction head than is required, and the pump will operate safely. However, if we increase the flow rate past this point, then we get into a situation where cavitation is going to occur because the NPSH available is now less than what the pump requires. So cavitation will start. So this is a critical flow rate above which cavitation is going to occur in that pump. Now, if these curves look familiar, there's a good reason for that. So I just want to review a place where we've seen something very similar to this before. So remember when we were talking about centrifugal pumps and piping systems, we said that the pump curve looks like this. So that's our characteristics of the pump, that's the pump curve, and the characteristics of the piping system were shown by the system curve, which looks something like this. So that's our piping system. And we said where those cross is the operating point. So if we take a pump with these characteristics and hook it up to a piping system with these characteristics, the operating point is there, and the flow that we obtain will be given by that value of Q. Now, notice some similarities between this. First of all, the axes are the same, head versus Q, head versus Q. However, when you look at these curves, the general shape of them is the same. However, they're swapped. Here, that is the characteristics of the pump. On this one is a characteristic of the pump. This is a characteristic of the piping system, system curve, and the NPSH-A is a characteristic of the piping system. So you see they've traded roles. That's a pump characteristic. This is a piping system characteristic. Now the other big difference here, if we take this pump and attach it to this piping system, it will operate at that location. So where those cross determines the operating point. However, that's not the situation here. If we take this piping system, hook it up to this pump, we don't automatically go to this flow rate. That's not what this means at all. What this means is if we're operating at some flow rate, let's say here, our NPSH-A will be there, our NPSH required is there, and we're operating in the safe zone. So we don't automatically operate here. That's not what this is saying. Whereas in this case, this pump hooked up to this piping system will operate there, but that's not the case here.